Okay, so let's show now that congruence, modulo, and ideal gives rise to a ring, namely the following. So suppose we have, I'm going to specialize the commutative ring, although it's not necessary. Suppose we have a commutative ring, I an ideal of that commutative ring, and we look at the set of cosets of I in R. So we have these two ways of notating this, either R mod I or R bar. I'm going to use R bar in the proof because I is understood. It's at the beginning here. And this set of cosets has a ring structure. In fact, it's a commutative ring, and it's called the quotient ring, or the quotient of R mod I. I'll say other ways of saying that in a little bit. But to say that it's a ring, we have to have an addition and a multiplication, and we have to say what the identities, the various identities are. So the additive identity is 0 plus I, the 0 in R plus I. That's like the 0 coset. The multiplicative identity is what you would expect. It's the multiplicative identity in R plus I. And the ring structure, the plus and dot, are, well, what we just did. So if we have two cosets, to add them together, we will add their elements. This is well defined. That's what the previous video showed us. And if we have two cosets, to multiply them, we just multiply them. Multiply what are called the coset representatives. All right, so let's prove this theorem. Proof. So let me just note that the previous two results prove that plus and dot multiplication, addition and multiplication, are well-defined operations. So we're not going to get anything sorry, we're not going to distract myself there for a second. We're not going to get anything weird, like more than one result for a product. So we've already proven that. So let's go through now the ring axioms. Let's go through additive. The additive axioms first. So the first additive axiom is that it needs to be associative, namely A plus I plus B plus I plus C plus I should be equal to associate the other way, A plus I plus B plus I plus C plus I. Whew. So we took three random elements of the quotient ring, and we have to add them together and see if we get the same thing. So let's put our orange question. On the left-hand side, we do the operation first on the inner parentheses, and the way to do that operation is you add B and C. That's what happens on the left-hand side. On the right-hand side, we have A plus B plus I, and then to that, we're going to add on C plus I. On the left-hand side, that's A plus B plus C plus I, and on the right-hand side, that's A plus B plus C plus I. And the question is, are these the same still? But R is a ring, so the elements A plus B plus C and the element A plus B and then plus C are equal. So are the cosets equal? Well, yeah, the guys that we're adding on the outsides are equal. So let's put a gold check mark through this. So yes, they are. All right, commutative. It's going to be very similar. So we have to ask, is A plus I the same as, plus B plus I rather? Is that the same as B plus I plus A plus I? And so on the left-hand side, we have a plus b plus I, and on the right-hand side, we have b plus a plus I. And again, these elements are just equal as ring elements, because R is a ring, and R has commutative addition. So since the elements outside the I are equal, certainly the cosets themselves are equal. And hopefully, oops, we want to use a gold there. That's not golden. We want to, sorry. So the way this proof is going to go is going to be very similar to how we proved Z mod M was a ring. And what did we do over and over again? We said, well, it's true in Z, and we're just sort of using the fact that it's true in Z to prove that it's true in Z mod M. And the same thing is happening here. It's exactly the same. So with that in mind, if we have some A plus I in R bar, then, well, what do we need to add A plus I to, oh shoot, I think I messed up my 3. Hang on a second. 3 is additive identity, sorry. So let me go back for 1 second. So given A plus I in R bar, we have, well, 0 plus I plus A plus I is by definition 0 plus A plus I, which is A plus I. Okay, and then similarly on the right-hand side, if you were to add it on the right, let's not add it as a new line, but similarly, if we were to add the 0 on the right, we would also get A plus I. Okay, so 0 is the additive identity. And then the last of the additive axioms is that if we have some A plus I in our R bar, then we have to find an additive identity. And I claim that additive identity is, or sorry, additive inverse, my bad. An additive inverse, I claim that additive inverse is negative A plus I. Well, why is that? Well, our rule for adding is you just add the guys out front. And A plus negative A is the additive identity, or additive inverse, sorry, I keep saying that. Negative A is the additive inverse for A, so A plus negative A is 0. That's the additive identity. Okay, so the additive inverse is negative A plus I. And I know it's the additive inverse because we proved that they were unique. Now let's look at the multiplicative axioms. All right, so associative. I'm not going to do associative. You do it. What's going to change? Well, you do the associative, look at the associative proof from before, and you replace all of the pluses with dots. That is it. So replace plus with dot in 1. 6. We claim it's a commutative ring. So given A plus I and B plus I in R bar, the multiplication should be commutative. Well, A plus I times B plus I is by definition oops, that's the wrong order. AB plus I, that's how we defined multiplication. And B plus I times A plus I is by definition BA plus I. But multiplication in R is commutative. So those are just equal because the coset representatives are equal. So we again get a commutative ring. Now this part is not necessary. You can quotient by you can quotient non-commutative rings, but you know, in this class, our primary focus is on commutative rings, and I'm just going to state that we stated the theorem with that in mind. So technically, we don't need this, and if you didn't prove this, if you didn't know that R was commutative, you would still get a commutative ring from it. All right, 7, a multiplicative identity. So we said what that was earlier. So given A plus I in R bar, 1 plus I times a plus I is 1 times a plus I, but 1 is the multiplicative identity in R, so that's just a plus I, and then similarly on the other side. And then we do a distributive property. I'm only going to do one of them because in a commutative ring, you just have to do one of them. So let's look at the left distributive property, and I'm going to stop qualifying where these elements are. These are in R bar. So we have to compute a plus I times b plus I plus c plus I, and we have to compare that to a plus I times b plus I plus a plus I times c plus I. All right, so when we do this, when we do the addition inside first, we get that. And now we apply the multiplication rule. I have to multiply the representatives, so the elements on the outside. And since the multiplication in R is distributive, we can rewrite this like that. So R satisfies the distributive property. All right. And now we have to look at a plus I times b plus I plus a plus I times c plus I. And that's ab plus I plus ac plus I, and that's ab plus ac plus I. Ah, they're the same thing. Okay, so distributive properties hold both the left and the right. Okay, so this was kind of long, but if you sit here and you compare this proof with when we showed that integers modulo m was a ring, the proof is almost exactly the same. We just have a slightly different language, that's all. Now, the upshot is that we can recycle that proof, right, from before, once we have the appropriate setting. And this is essentially what's happened. So if you were to go and you were to compare the two, you would see they're almost exactly the same, changing what needs to be changed. But nevertheless, R mod I is a ring, and so that's the end of our proof. So we refer to R mod I, or R bar, however we want to write it, as the quotient of R by I, or as a quotient of R, or as R mod I. All of these things will mean the same thing, and I'm sure there's other ways that people refer to these quotient rings that we get, but I will use this language.